Okay, welcome to a new talk in the virtual seminar of geometry with symmetries. We are happy because 2 days ago was the birthday of the seminar, 4 years already. And actually there will be a distinguished lecture on June 5, let me check, June 5, given by Robert Bryant. Okay. And in this opportunity, it's a pleasure to introduce Juan and Sebastián Rodríguez from Pontificia Universidad Javeriana in Bogotá, Colombia. And he will talk about isospectrality in symmetric space. Thank you, Juan.
Okay, thank you. Thank you for the presentation and, of course, for the invitation. It's a great pleasure for me to be here in the seminar. Okay, I'm going to talk about isospectrality in symmetric spaces. This is a joint work with Emilio Lauret. So let's begin. So first, I'm going to talk about the preliminary, some results related with our result. And we also are going to talk a little bit about homogeneous geometry. Then the idea is to define two families of metrics into manifolds. So we are going to study this manifold. We are going to define a family of metrics, and we are going to prove some results in uniqueness or in spectral uniqueness, and the same in this manifold. So let's begin. This talk is based in the following article, the spectrally distinguishing symmetric spaces, part 1, with Emilio Lauret, and this is available in archive. So let's begin. So isospectrality. So our setting, we begin with a compact Riemannian manifold without boundary, and we consider the Laplace Beltrami operator, the gradient of the divergence of the gradient. And we consider this operator in functions. So one knows that the spectrum is the spectrum of this operator, the eigenvalues of this operator. So we have the zero eigenvalue because of the constant functions, and we have the rest of the eigenvalues, they are all positive, so we can order them. We take lambda1 the first, lambda2 the second, and so on. One knows that this sequence of real numbers goes to infinity. So the problem in which we are going to deal with is this. Can we hear the shape of a manifold? That means that we are going to study if the, okay, this question comes from physics, where one asks if you can know the shape of a drum, knowing the frequency in which this drum can vibrate, right? So in the context of Riemannian manifolds, the frequencies are modeled with the spectrum, right? So we ask if two manifolds in which has the same spectrum, two manifolds with the same spectrum, we ask whether they are isometric, whether they have the same geometry or not. So if we have two Riemannian manifolds, we say that they are isospectral if the spectrum are equal. And of course, with this generality, this question is false. There exist examples of isospectral Riemannian manifolds that are not isometrical. And there are techniques to build this, to construct examples of such manifolds. So what the general question we are going to deal with is, are distinguished manifolds uniquely determined by its spectra? When we say distinguished, is, for example, Riemannian symmetric spaces or homogeneous manifolds with special geometry. So now we are dealing with manifolds with a special geometry, right? So in this generality, the strongest result that I know is the theorem of Tanom, that says that the round sphere is spectrally unique for n less or equal to 6. When we say spectrally unique, is in the class of all Riemannian manifolds. That means that if we take another Riemannian manifold with the same spectrum, then it has to be isometric to the round sphere. So this implies uniqueness among all Riemannian manifolds. However, only a few results regarding spectral uniqueness are known. So usually it's interesting to consider uniqueness restricting the family of metrics. We don't ask uniqueness among all Riemannian manifolds, but we restrict the family. So in this direction, we have three partial results. So Gordon, Schutt, and Sutton proved that every invariant metric on a compact Lie group K is spectrally isolated within the left invariant matrix on K. That means that we're restricting the family of metrics to the left invariant matrix on K. And we ask if the invariant metric is unique or not. And they proved that there's a neighborhood of the invariant metric in this class of metrics where there are no isospectrality with the invariant metric. Also, Lauret proved that the invariant metric on SPN is spectrally unique within the left invariant matrix on SPN. Again, here we're restricting the class of metrics to the class of left invariant matrix on SPN. Okay. Now, this last result, Bettioli, Lauret, and Piccioni proved uniqueness in crosses. Crosses mean compact rank 1 symmetric spaces. That means that uniqueness within the space of homogeneous metrics. That means that if we have two homogeneous metrics in these spaces, Sn, Rpn, Cpn, Hpn, and OP2, those are the compact Riemannian rank 1 symmetric spaces, then if we have two homogeneous metrics in these spaces, they have to be isometric. And in this talk, we are going to do that. We are going to take a family of metrics in two manifolds, and we're going to ask about uniqueness of the metric within that family of metrics. So let's begin with some basics of homogeneous geometry. So let MG a compact Riemannian manifold, and it is called homogeneous. I hope that everybody knows that, if the isometry group acts transitively on M. So we want to study homogeneous metrics in a manifold. So how do we classify homogeneous metrics on a fixed manifold? The usual way is the following. We take the compact Lie group acting transitively on M. And we take H to be the isotropy group of G at the point P. When we take these two, it is well known that the quotient, G quotient H, is diffeomorphic to M by this diffeomorphism. And what we do is we take a complement, PA complement at H invariant complement of H in G. That means that we can write G as H plus P where P is at H invariant. In this context, it is well known that P is isomorphic to the tangent space at the point P, right? By this isomorphism. And with this correspondence, if we want to study G invariant metrics, G, this means that G acts by isometries. Then we have to study at H invariant inner products in P. Note that if G acts by the isometry and G acts transitively, the isometry group also acts transitively, which means that this isometry group is homogeneous. So if we want to study invariant metrics, we need to study at H invariant inner products in P. So if we want to find all homogeneous metrics on M, we need to classify compact Lie groups that act transitively on M. And after that, we can study J invariant metrics. And that gives homogeneous metrics. Okay, let's continue. So in this direction, we need to study groups acting transitively. This is a hard problem, so we restrict the groups to groups in the following way. This is a result by Onichik that says the following. If we have a MG, a compact irreducible symmetric space with rank greater or equal to 2. The rank 1 is already solved the homogeneous matrix of rank 1 by Lauret, Pichoni, and Bettioli. Simply connected and not a group type. This means that M is not a Lie group with a invariant metric. And if we take a subgroup of the isometry group that acts transitively, then we have few cases. We have these first possibilities. We have these two families of manifolds, and we also have these two Grassmannians. So in this talk, we are going to deal with the first two. We're going to study, so here we have the manifold, and then we have G is the subgroup acting transitively, and here we have the isotropy, and the same for the second one. So we're going to deal with metrics, J invariant metrics for this G in the first case, and the second case for this G. So the question is there isospectrality within the space of J invariant metrics? We're going to restrict to that family of metrics. And the strategy to solve this question is to compute the first eigenvalue, maybe the second, and to use also the volume and the scalar curvature. Because these two, since the manifolds are homogeneous, since we are studying homogeneous metrics, these two, the scalar curvature also is spectral invariant. So we are going to compute some of them, and we are going to ask, we're going to try to distinguish two manifolds in these families because of those values. So the first case, this is the space of complex structure in R2m plus 2, and we can present as this quotient. And of course, we have G, the subgroup acting transitively, and we have the isotropy. So the usual way, as we say this, we take a complement of H. H is UN, and we found that the complement has two irreducible components. So G is H plus P plus M, where this is P and this is M. And P and M are non-equivalent, irreducible, and the H invariants of spaces. So if we want to study metrics, we have to put an at H invariant metric inner product in P plus M. So the space of J invariant metrics, as we said, we need to put an inner product in P and P plus M, but since P and M are not equivalent, the metric is a multiple of any in P and in H is a multiple of any at the H inner product. So we can take the negative of the killing form of G. Remember that G is SO to M plus 1. We take the killing form, and in P has to be a multiple of this inner product, and in M has to be a multiple. So we can vary this multiple, and we have all the at the H inner products that corresponds to J invariant metrics. So here we have the following. Note that if we take H plus P, we have SO2N as a subalgebra. We have a subalgebra which is isomorphic to SO2N. And we can take K to be the connected subgroup of G with Lie algebra K. This K defined by H plus P. And in this context, we have the following. We have H is contained on K and K in G. And this is going to help us to solve the problem of studying the spectrum of the matrix. Some notations. So, if G is a completely group and we have two representations, unitary representation of G, we are going to denote first G hat denotes the set of equivalence classes of unitary irreducible representations of G. We are going to denote by this sigma tau the dimension of the Javerian morphisms from sigma to tau. Of course, if sigma is irreducible, this number counts how many sigma appears in the composition of tau as irreducible representations. We have also the space of a spherical representation of the pair GH, which means those representations that has fixed points for H. The representation where the set of fixed points for H is not zero. And we will denote, okay, we have the Casimir element in the enveloping algebra, universal enveloping algebra. And this element, if the representation is irreducible, this element acts by a multiple because it's in the center. So we are going to denote that multiple in which acts minus the Casimir element by lambda sigma. And with these ingredients, we can describe the spectrum. So it is well known that the spectrum of GH with this metric that we construct consists of the union of the eigenvalues of this operator. Here we are taking the Casimir element of G, but with the bilinear form that we defined in P. Okay? And so consists of the union of the eigenvalues of P minus this operator restricted to BPH. This is the set of fixed vectors by H, where P is taken in the spherical representation of the pair GH. So this space is not zero. In our case, we have H contained in K. This is a subset of G, a subgroup of G. So in this case, we can reorganize, we can compute these eigenvalues of this operator. This is made in a paper by Emilio Lauret and Piccioni. And the spectrum consists of the eigenvalues in this formula. So here we have this lambda tau is, as I said, is the multiple by in which the Casimir minus the Casimir element acts for the representation tau, and this for the representation P. Where here we are taking the representations, P has to be an irreducible representation in the spherical representation for the pair GH. And tau has to be a representation in K such that when we restrict P to K, this is a representation in K, it may not be irreducible. So tau has to be an irreducible representation that appears in the composition of P restricted to K. Remember, this number when tau is irreducible counts how many tau appears in the composition. And we also have a formula for the multiplicity. The multiplicity in which this eigenvalue appears is this. So what we need to do now is for the metrics that we construct, we need to compute first the spherical representation, GH, then we need to compute for those spherical representation, we need to compute what representation of K appears in P when we restrict to K. And then we need to compute the Casimir multiple, the lambdas, tau and lambdas P. So the first problem is to compute the spherical representations. How we do that? We have GH is the pair. Remember that GH is the pair SO2n plus 1 is G and H is UN. So note that a representation is spherical. A G representation is a spherical representation of the pair GH. If there exists a spherical representation in the pair KH, such that when we restrict P to K, it also has to note, we have P, right? We restrict P to K. It also has to have fixed vectors for H because P has. So there exists a representation tau in an irreducible representation with fixed vectors in H. So P is in GH if and only if there exists an irreducible representation tau with fixed vectors in H such that appears in the decomposition of P restricted to K. And why we say that? Because the red condition to be a representation in KH is well known because K is SO2n and H is UN. That's a symmetric pair. And the spherical representation of symmetric pairs are well known. And the blue condition is P restricted to K is, okay, tau is a representation in SO2n and P is a representation in SO2n plus 1. And that are also well known because those are the branching laws for the pair SO2n plus 1, SO2n. So we are taking advantage of that, and we are considering the red condition and the blue condition. And those conditions are expressed in the weights, with the maximal weights. So let T be a maximal torus of K, since K and G has the same rank. It is also a maximal torus in G. And we have the epsilon 1 and epsilon n to be the canonical basis of the Lie algebra of T, dual complexificated. So from the restriction laws of the pair, of this pair, as I say, this one, SO2n plus 1, SO2n, we're going to use this for the blue condition. And for the pair SO2n and UN, here we need the spherical representations. We have the following. We have the spherical representation of GH can be expressed by this set. This is the P lambda, where lambda is the maximal weight of the representation P, where lambda, we write lambda as A1 epsilon 1 plus A epsilon n. And the red conditions say that there exists a representation in K. Let's write this representation as B1 epsilon 1 and Bn epsilon n. And the red condition says that that weight mu has to be in this set, where these are the fundamental weights. has to be in this set where the W tilde is epsilon 1 plus epsilon p, W tilde p. We found that the red condition, and the blue condition, it's for that representation to appear in the representation P restricted to K. And this is a branching law, which is the blue condition. So we need to have these two conditions for the spherical representations. And we are going to work with this. And in this case, we also have that the multiplicity of the the times that tau lambda appears in P lambda, here I missed restricted by K, is 1. Here, this number is tau lambda, P lambda restricted in K. So, we found the spherical representation. Then what we have to do is to compute those numbers lambda, P, and the lambda that is the multiple in which the minus Casimir acts in the representation. And for that, we use the Freudenthal formula. That says that multiple is the inner product of lambda with lambda plus 2 times rho, where rho is this number, a half of the sum of the positive roots in the algebra. We compute that. We already have lambda. It's defined by the A's. And we have the B's define the lambda tau, define the representation tau. So we also can compute the lambda tau. And we compute this, and that's the formula. And putting all together, we can describe the spectrum. So we have that the spectrum has to be this expression over there. And of course, we need the condition. Remember that mu is represented by the B's, and the A are the lambda, the capital lambda. So we have this condition. This is the formula for this condition. And the theorem, after we have that formula, we have a description, an explicit description of all the eigenvalues of the spectrum. So we can compute the first one. We take that formula and we found that the first eigenvalue is given by this formula. It's the minimum between these two values. How we compute the minimum? It's easy once you have the formula, because we split into cases. If mu is different to 0, well, you can see the formula. Remember that mu is defined by the B's. So we have this second summand, and we want to make it minimum. But since the blue condition, the A's are greater than the B's. If we want to make minimum, we can ask to the second summand to be 0. Which happens when the A's are equal to the B's. And then if the second summand is 0 and we want to find the minimum, we see just the first summand. And for that, once you see that this is increasing in each BI, so it's minimum when the BIs are minimum. So the resultant expression is increasing in each BI, and it's minimum for the red condition. The BIs are minimum when B1 is 1 and B2 is 2. That is that second expression. That's why here appears P epsilon 1 plus epsilon 1. This is the minimum for the B's when the B's are not 0. And tau epsilon 1 plus epsilon 2 because the A's are equal to the B's. I said it wrong. The taus are the b's and the p are the a's. And then if we want to find the minimum of that expression, now we suppose that mu equal to 0. We see the expressions. Remember, mu are the b's. If are 0, this first part doesn't appear. So we have the second. If the b are 0, we see that again, this is okay. Since the b are 0, the blue condition says that the i's have to be all 0 except the first one because of the blue condition. And so we only have that the first one is not 0, so lambda has to be k times epsilon 1. And if we replace here, we see that the resultant expression is increasing in k. So it has to be minimum when k is equal to 1, which is the first expression. Lambda p epsilon 1 tau 0, which means b equal to 0 and a equal to 1, just the first one. And we replace those values and we have these two numbers. So the first eigenvalue we could compute it is the minimum between these two expressions. So the theorem is that we found spectral uniqueness within that family. That means that if we have two manifolds in that family, let's call MGR1S1 and MGR2S2, then if the spectrum is equal, then they have to be the same metric. R1S1 has to be equal to R2S2. And we prove that using the value that we just compute. We found lambda 1, we used lambda 1, and we find a similar formula for lambda 2. It's a long formula, so because we need to consider cases depending where the first eigenvalue is achieved. So we use the first formula and the second formula, and these equations along the volume condition imply the result of spectral uniqueness. And the volume condition is this second one. So we would use that formula that we put here, lambda 1 and lambda 2, and we also had to compute some multiplicities. And that led us to distinguish two manifolds within the family. And that ends with the first case, with the first family of manifolds, of metrics. And in the second family, it was a little harder. We take M, this is so for the second family, we take M as the SU2M plus 2 as Pn plus 1. And remember that in the theorem, we say that we have G as the group which acts transitively to be SU2M plus 1. And the isotropic group was SPN. So we take this and we write, again, we need to decompose, to give this decomposition of G as H plus an at H complement. And in this case, we found that we have three irreducible components, non-equivalent. So here we have H, the Lie algebra, and P1, P2, and P3. And we are going to do we're going to compute it in a similar way than the first one. But the difference is that we have three components here. So since we have three irreducible components, not equivalent, we can describe the space of J invariant metrics again in this way. So now we need three numbers, R1, R2, and R3. And in each component, it has to be a multiple of the Killing form, the negative of the Killing form of H, which also is at H invariant. And by the irreducible, it has to be a multiple. In each component, So we call this multiple like 1 over R1 square, 1 over R2 square, and 1 over R3 square. And in this case, we can construct two intermediate subgroups. So we know that if we take H plus P3, this is SU to N. And if we construct K as H plus P3, which is H plus K prime plus P2, this is P2, this is SUN plus U1. We have these two subgroups, two subalgebras, sorry. So these are subalgebra of G, and again we denote by K prime, which is isomorphic to SU to N, and K, which is isomorphic to SU to N times U1, the connected subgroup of G with the algebras K prime and K respectively. So in this context, we have H is a subgroup of K prime, and K prime is a subgroup of K, which is a subgroup of G. And we proved a similar result to compute the eigenvalues of the Laplace-Beltrami operator. So in this case, we have the following theorem. So the spectrum consists of these eigenvalues. We have this formula, which have lambda p again, which is the lambda p is the Casimir element, the multiple in which the Casimir element acts, minus the Casimir element. Here the same, and we have this lambda tilde tau, which is lambda tilde is, you can see that the K has center of dimension 1. So lambda tilde is going to be the multiple in which an element in the center, unitary element, acts, minus the element. The same with the Casimir, but with this element. And this is obtained again by reorganizing the eigenvalues of the dot operator that we had before. So now we need to compute. Again, here we have that P has to be an spherical representation of the pair GH, and K has to be an irreducible representation. Tau has to be an irreducible representation in K, such that appears in the composition of P restricted to K. So again, we need to compute this first GH, which are the spherical representations, and then we need to compute the lambdas. And we did that in the same manner. So in this case, what we need to use is the restriction laws of this pair, which are very well described in a paper by Lauret and Miatello. SU to n plus 1, SU to n times U1. And we need to use the representation of SU to n SPN. Okay? So using these two that are well known, this is a symmetric pair, we can parameterize all the representation, the spherical representation, and we also know what representation appears when we restrict P to K, and we also know how looks tau when we restrict to K prime, where we parameterize that with Q, which are n-1 natural numbers, K, which is an integer, and L, which is a tuple of n integers, natural numbers, and the formula was this one. So lambda, that's a very long formula. This projection is a projection of the roots from U to n plus 1 to SU to n plus 1. This is very well described in a paper by Lauret and Miatello. So we have this formula. Here, this capital QI is a number that depends on Q and on I. It's the sum of the elements of Q until the I component. We have this lambda I are the components of L. Sorry, these Li are the components of L, and we have these three. So this is the weight. Yes.
Juan, just a comment. This branching law is very well known. It's not doesn't belong to Lauret and Interior.
Okay,
It has been
sorry.
known for a while.
Okay, this branching law is very well known. So lambda, we have this formula for lambda, mu, and mu prime. And of course, we need a condition, which came from the branching law and from the spherical representation of this pair. We have this condition with the L, K, and the Q's. So that was a long computation to achieve these three formulas. And so if we put together in the formula that we compute in the theorem, we have the eigenvalues, where it's R1 squared times this expression, where this expression is a very long expression. Again, this Q tilde is a number that depends in Q, in the vector Q. And the same L is a number that depends in the vector L. And these three expressions. And what we need to do after that is to compute the first eigenvalue. So we have this formula, and we have to compute the minimum of this. That was a little bit long, but we achieved the following formula. So lambda 1 has to be the minimum between these four expressions. I didn't put the proof here because it's a long computation, but we have these four expressions. So the next question that we try to solve is whether there is uniqueness within that family or not. And we couldn't prove that in general for two arbitrary metrics, but what we proved was uniqueness for the symmetric metric. Of course, in that family, we have the symmetric metric, and the symmetric metric is taken by when we take these values. R1 equal to square root of 2t, and R2 equal to square root of 2n plus 1 divided by n plus 1 times t, and R3 equal to t. This is the family of symmetric metrics. And this is spectrally unique within the space of metrics G, R1, R2, and R3. And the proof, I mean, this is not the proof, this is the idea of the proof, a very vague idea. What we need to do is to analyze the first eigenvalue and the volume. So the idea was, we have these expressions. So this metric attains lambda 1 in two of these expressions. So we analyzed the multiplicities, and we proved that if we have another metric, GR, with the same spectrum, because of the multiplicity, it has to be attained also in the same two expressions. So that gave us two expressions in R1, R2, and R3. That if you see that like in calculus, that's a plane in R1, R2, and R3. And the intersection, we have two equations with R1, R2, and R3. So in the intersection of these two planes has to be a line. So we parameterize the line, and after that, we use the volume condition, and we put into the formula condition. That's a formula in one parameter, and we found that that parameter has to be the same that in this metric. That was the proof. Once that you have this long expression, it is not very hard to prove that the first eigenvalue, that it is not hard to prove that the uniqueness in the symmetric metric. But we couldn't prove that if we have two metrics within that family, it has to be unique. We couldn't prove that. just for the symmetric metric. Okay, that's what I wanted to say. And this is the reference. So the first one is the article in which this talk is based. You can find it in ARCA. You can find the details of the computation there. Here, this second one is spectral isolation of invariant metrics. As we say, this is that result for isolation of the invariant metric within the left invariant matrix. And these two, from Emilio Lauret and Piccioni, are for crosses. Those are the papers where they proved the uniqueness of homogeneous metrics within crosses. And most computation are based in these techniques using representation theory of Lie groups. And this Megan Kerr here studied those metrics that we present today, but she made some computation also with the scalar curvature. We didn't use the scalar curvature, but they are computed here, and of course that metrics that we present, they are present here also. And here is the place where we studied the spherical representations of the pair SU. Those that Lauret told that is not of them. Okay, that's what I wanted to show you today.
Okay, thank you very much, Juan. Very nice talk. Are there questions? Hi, Rod.
Thank you.
You're muted, Rod. We cannot hear you.
Sorry?
No questions, just.
I'm sorry. I have a comment, Juan. The article by Megan Kerr was very, very important to the article, right? Although she didn't study the spectrum of any metric, she was looking for Einstein metrics, and the study of the delicate study of the G invariant metric on those spaces was done by her, so it was quite important. Okay, are any questions or comments?
And now we are still working. I want to tell that we are still working in the other cases. We have this in the Sonic theorem. We have these two other cases. We are studying those now. For the second, we already proved that the symmetric metric is unique, and we are working in the fourth one.
Okay, if there are no questions or comments, we thank Juan Sebastián again. Thank you, Sebastián.
Okay, thank you very much for the attention.
Thank you.